morning. I can tell it's Saturday morning. Excuse me. A couple of classroom rules. Questions are mandatory. Do we have anybody sitting in the back row? Oh, yes, we do. Okay. Second of all, if I lapse into acronymese, please ask me what I'm talking about. It's a disease that everybody inherits working at the test site because of the type of work that we do. And again, questions at any time, feel free to interrupt me and ask your question. So I'm going to talk about the formation of the Continental test site. Any history majors here? Technical? Well, there'll be a couple of pop quizzes here, so you laugh. So let's start out. During World War II, the Navy did not participate in the development of the fielding of the nuclear devices which were dropped on Japan or anything. And they really didn't know how to deal with, or thought they knew how to deal with having to operate in a nuclear theater. And so immediately, as you can look at the date, this is even before the surrender of the Japanese, they were asking to have some tests performed so that they could better understand how they would need to operate in those fields. You notice this guy's name? No relation. So what they decided to do was they were going to do 3 tests. They originally asked for 2 and they're going to do 3. We'll talk about those tests in a little bit. But they actually put this together. They put together a joint task force. This was called Operations CROSSROADS. And it was formed in early January of '46. And the spot they chose to go to was Bikini Atoll down in the Marshall Islands. And we'll try to give you a picture of where that was. One of the tests was going to be in the atmosphere, a drop from a bomber. One was going to be shallow underwater, about 90 feet underwater. The lagoon where they were going to do these tests was about 180 feet deep at that spot. And finally, they were going to do one out several hundred feet underwater, which got canceled. So you can see the lagoon here. Here's Bikini Island. And here was the target area where they were going to do all these tests. So to orient you a little bit, Hawaii, Marshall Islands, about 2,500 miles across there. So as I say up here, it's a long ways to the hardware store when you forgot that favorite screwdriver that you need. And this added all sorts of complexity to the test because you really need to think of everything that you need or might need or hope that you don't need. And this turned out to be a very, very big task force. As you can see, over 42,000 people. Now, they were all on ships because the Marshall E's who were on those islands had obviously been moved off Bikini and a couple of the islands which were close by. So all these people on ships, there was 140 some supply ships. And in the lagoon, they set up this array of targets ranging from the USS Nevada, which was the ground zero for the airdrop, down here, Independence aircraft carrier, another aircraft carrier, heavy cruisers, another heavy cruisers, landing craft, submarines, German battleship. There was a Japanese, and I don't see it on there, Arkansas. Again, a whole array of ships because they were trying to understand what would happen to these ships. And they really didn't have much of an idea of what was going to happen. Big deal, international audience. Even the Soviets were invited to come, press, news media, on and on and on and on. And they spent $100 million in 1940 money, or in today's money, that's about $1.3 billion. And remember that number, because we'll do it to comparison here in a minute. So they did the first test, which was called ABLE, in July 1st of 1946, and this was an airdrop. And the devices they were using were exactly the same device which they had dropped on Nagasaki. That's a plutonium implosion device, which they had tested at Trinity. And so because this was such a big deal, the Army Air Corps held a corps-wide bombing competition to pick the very best crew out there to conduct this test. So they did that. Plane takes off. They get over the target. They make several runs to make sure everything's exactly right. Finally, they make the bombing run, and they drop the bomb. And they're aimed at the USS Nevada, because it's a surplus ship. And to make sure they had a really good way to tell it, the whole ship was painted a bright red or a bright orange color with some white crosses on it. So there's absolutely no mistaking which ship they were going to have as a target. So they drop the bomb, and the bomb goes off, and they missed the target by half a mile. Big controversy. They were never able, or there was, let me put it this way, there was never a published answer of why they missed the target, but they missed the target. The problem was, by missing it by that large, a lot of the instrumentation they had set up was obviously focused on the USS Nevada, and they didn't get a whole lot of data off this. Also, it sank a few ships and damaged some, but overall, it wasn't such a big deal, and the Navy's thinking, well, not too much different to operating in a nuclear war zone as they're in a conventional. Next shot was Baker. Show you a little video. This is something off of YouTube. The reason I chose this is because it's fairly high definition. There's only a little bit of sound in here. When you go look at this on YouTube, it's got some of this dramatic music playing, blah, 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 blah. So here's the container that the device was in, about 90 feet below the deck. And if you watch right there, this is a shock wave going out from the test. This is sand, seawater. You can see the ships scattered in the lagoon. Again, sand and seawater. So this column is about 2,000 feet across and goes up about 6,000, 7,000 feet. And in there is anywhere between 2 and 10 million tons of water and sand, seawater and sand. And in those days, everything that went up off the earth came back down. So that all had to come back down, and it formed what we call a base surge, which was several hundred feet high at ground zero, and that washed over all of these ships.
No, there's no surrounding
they were manned by animals.
Had become seriously radioactive and could not be safely approached for some time. This effect was not anticipated, and ultimately led to a decision by President Truman to call off a third deep underwater test, codenamed Charlie.
USS Nevada. That's a submarine, was on the surface. There's the Independence, the aircraft carrier. You see all these guys climbing up on this thing. When that device went off, it irradiated and contaminated essentially all the water and the sand in the lagoon. And very, very intense. In fact, so intense that they couldn't get back on the ships for several days. Created a real problem because, as you can see, they were trying to decontaminate these by spraying water. Well, to decontaminate something, you have to have something that's clean to wash the contamination off. There was no clean water around. So what they were doing is they're spraying contaminated water on contaminated ships. Probably not a great result. Also, they didn't have very good radiological control, so not only were they exposing the sailors trying to do this work to radioactivity, but they didn't have good control of the people coming out of those ships that were contaminated, and they were coming back and they were contaminating where the ships where they were leaving. All those ships have seawater systems on them. That systems was getting irradiated and contaminated, and it was a real disaster. But the Admiral Blondy, who was in charge of this task force, was having a hard time understanding the effects that this contamination could have on people. And the senior radiological control officer, who was from the Los Alamos Scientific Laboratory, was having a hard time talking to him about what was going on. So here you can see again using fireboats to try to decontaminate these ships. Again, not successful at all. So what he did is he had his crew go out and they caught a sturgeon fish in the lagoon. And what you have here is what we call an audio radiograph, where the source for the radiation is the target itself. So they took this fish, they laid it down on a piece of photo paper, exposed it, developed that picture, and what you can see here is this is a fish, this is the internal parts of the fish. So they had taken an X-ray of this fish just for the contamination of water. The Admiral understood that. And so within a period of a week, they packed up and went home. The vast majority of those ships which were in that lagoon were either sunk in that lagoon or taken over to Eniwetok, but used for tests over there. Or they took a few back to Hawaii and San Francisco to see if they could figure out how to decontaminate these. And they were not very successful at all. Well, now the Navy's got a real problem, because now the whole world knows, how do I contaminate a whole fleet with one bomb? So much so that they canceled the third test because they needed to solve this issue that they had first. So we moved forward from that, and in early 1947, the Atomic Energy Commission is formed. Up to that time, the military was in control of the nuclear weapons program, and there was a growing concern about having the military be in charge of that. So with the formation of the Atomic Energy Commission, it now went under civilian control. As you all may know or not know, any detonation of a nuclear device by the United States must be authorized in writing by the President of the United States. So when we conducted a test out of the test site, what he did was sign off on a test series for those tests, but it took the President's signature, which allowed you to finally conduct that test. You can see Chairman David Lithenthal was on this, was the first commissioner. So let's jump to 48. 48, Los Alamos National Laboratory has been working on new and better designs and efficient. Obviously the first devices were very, very big, 10,000 plus pounds. You could only carry one per bomber type of thing. So they had been working on this and they wanted to test some of these concepts. So they put together another task force. This one is different in several ways. Number one, it is under the control of Atomic Energy Commission, which is a civilian organization, and they went to Eniwetok, which is in the same vicinity, but a different island. Army general in charge of a task force, significantly fewer number of people on this, and they conducted 3 tests, as you can see there, and not airdrops from towers, because with airdrops, as was demonstrated in the first one, you don't know exactly where it's going to go. So having your instrumentation try to focus on that is very difficult. You have to have much wider fields of view. If the device is stationary, like on a tower, much, much easier to do that, get finer resolution in your data. So a few facts, 10,000 people, certainly a smaller number, 260 million in current year dollars versus the 1.3 billion that we had before. And they conducted the 3 tests that you can see here, yoke, zebra, and x-ray. All new types of designs. After they conducted the first test, they were looking at issues that they were having. And one of the things I point out to you here is logistics, weather, safety, security, and extremely high costs of conducting those tests down there. The weather in the South Pacific is terrible. The problem is it's so variable and it changes so much. The wind can be blowing from the north and 5 minutes later it could be blowing from the south, and 5 minutes later it could be blowing back from the north. So a very difficult time in predicting what the weather is going to be for one of these tests, and they would change, and we can see results in later years of doing larger tests down there, the consequences which came out of that. So somebody said, the other thing was, it took such a logistic supply chain to get there, and you also, once you went, that's what you had, and you couldn't make some changes. As you learn something from a test, you might want to change what's going to happen on the next test. Very difficult, if not impossible to do, because you're so far away from everything. So somebody said, so what if we had a test site on the continental United States? Good political answer by the Atomic Energy Commission. Complete weasel words about that. Sounds like a nice idea, but geez, we don't know, type of thing. It would be desirable. But issues, here's especially dangers inherent in misunderstanding what we're trying to do. Trying to determine this should be classified. So you go forward. This was the military's organization that dealt with nuclear weapons back in the early days. They were tasked to put together and do a top secret project called Operation Nutmeg in 1948. And as you can see, what they were trying to do was determine, could it physically be feasible to do nuclear tests on the continental United States and do them safely and securely without a lot of issues, especially from fallouts. As you can see, he was only supposed to do how, when, and where type of thing. So he did that. And he came up and said, if you chose the right spot, and he circled some large areas within the United States where he thought that was possible, you might be able to do this. As you can see, southwest or the humid southeast, we'll talk a little bit about both of those, but he really liked the southwest because of primarily weather conditions and also the lack of population. One of the places which you pointed out we'll talk about was on the East Coast, Carolinas, around Camp Lejeune, because as you know, the weather in the United States, typically the wind blows from west to east. So if you're on the East Coast, it would blow any radioactivity and fall out over the ocean, or so it was thought. I have a couple articles that I found out of that area which says that's not true in that area. The weather there is, again, not real predictable, but they get a lot of circular flow in there where it'll go out over the ocean and then come back over the land. Notwithstanding that probably at that time, half of the population of the United States lived within 500 or 600 miles of that. Again, but it didn't talk about these type of things. Again, he was trying to determine, could you feasibly do this physically? Lots and lots of discussions, and they finally said, hey, the American public is just not ready for us to drop an atomic bomb on the United States, continental United States. So it was tabled. In fact, they used the word a national emergency. Well, the national emergency is coming. First of all, the Soviets in late August of 1949, much to our surprise, because we had said Soviets are going to need 20 years to figure this out, because we had a very low regard of their scientists, which was not true at all. Their scientists are top notch. They've always been that way. What they lack is the support to allow them to realize what they can think of theoretically. But anyway, they tested on August 29th their first atomic device, which looked exactly like ours, because it was a copy, courtesy of a couple of gentlemen, Fuchs and Hall and a couple others, who provided them all the information. Now, Stalin's scientists told him, or were keeping him involved with their nuclear weapons program, of what they were learning and stuff like that. But Stalin, being Stalin, didn't trust anybody. And he didn't especially trust his scientists. But when the spies came back with information, and the spies told him the same thing that his scientists did, he said, oh, well, maybe that's right or not. But he also was supposedly said, if this doesn't work, I will find a team that can build one that will work. Well, if you've got a proven design already from the courtesy of the US, are you going to put yours out, and if it doesn't work, you're headed to the gulags at the best, or probably being shot, or are you going to use a proven design? Obviously, that's what they did. But we grossly underestimated their technical ability. Second of all, we were already moving into the area of looking at designing a thermonuclear weapon. The first atomic bomb is a fission device where fission is splitting heavy atoms apart and releasing energy. Fusion is pushing light items like hydrogen together and fusing them together, much larger energy release. But this would require additional testing before they wanted to go to the South Pacific. And then third, in June of 1950, we enter the Korean conflict. And as you can see, the military really wasn't very prepared for this, and they told the Atomic Energy Commission, I'm sorry, but we may very well not be able to support you in your area. And by the way, where you're going down there, we're not quite sure how this conflict is going to go, so we may not have the absolute control of that area, which we will need. So if we look at this raised people, so the national emergency comes about because Truman, in December 16th of 1950, declares a national emergency because of the Korean War. So they drag Nutmeg off the shelf and they go back and look and they identify, I have 6 areas on here. The book says 5, but when I counted it's 6. Here's this Cape Fear, Camp Lejeune, the Gulf Coast. These went away almost immediately. Primarily, as you can see, not a lot of government-owned land and lots of population. Alamogordo, that's where Trinity was first conducted, or in that area. Dugway up in Utah, and then in Nevada there was 2 areas, one down where the test site actually is, and then one up in northern central Nevada. So like I said, through a series of studies, they finally focused on the one in the southern. The Las Vegas and Gunnery Range was there. At that time, it was several thousand square miles. We had been put together for World War II. Very desolate area, as you know about the test site. But very good weather. Very predictable on the weather, and you know, relative to having to go 2,500 miles or a couple hundred miles, big difference in logistical support. So they evaluated these areas, you know, for fallout patterns, prevailing winds, primarily weather, and also what we would call downwind populations. So as I said, in December 16th, Truman declared a national emergency for the Korean War. December 18th, he signed this top secret letter, of which he withdrew about 340 square miles of land from the bombing and gunnery range from, at that time, now as the Air Force, and gave custodianship of that to the Atomic Energy Commission. There's these dates, December 18th. January 11th, they tell the public, oh, we have this test site, we're going to do tests. Put these warning signs all up the area saying, you really shouldn't go in here because we may be dropping an atomic bomb in your head without warning. He approves Operation Ranger, which we'll talk about in a minute. And by the way, he tells all the local officials around him, oh, we're getting ready to detonate nuclear weapons in this area. No infrastructure out there at all. First test series, Ranger. First test, January 27th, 1951. You can see the details, dropped from a bomber coming out of Albuquerque, 5 tests. Oh, look at the cost, $26 million for 5 tests. So if you do that, they spent $2 million in that year's money. There was CROSSROADS, compared 1.2 billion to the 26 million. Different yields on these tests. The target was a bunker which they built to withstand up to a 10 kiloton direct hit. Instrumentation was in there for looking at the performance of the device, what they would have to do when they dropped the larger ones, or they would have to go back and clean some stuff up. That's why you see a day or two advance. But they essentially did 5 tests in 10 days. So that was the first test series at the site. It was developed. They were going to do things campaign style, but campaign like they were doing in the Pacific, because that's how they knew to operate. But they soon realized by having it here in the United States, they could run it on almost a continuous basis. They had another test series in 51. And from there on out, they developed the infrastructure and conducting testing essentially year-round. The test site has grown. You can see facts and details on that. The Test site now is about 1,375 square miles, slightly larger than the state of Rhode Island. We are completely surrounded by government-owned property, primarily the Nellis Bombing and Gunnery Range, on three sides, because again, it's several thousand square miles. BLM is on one part of one side. So I thought I was going to ask you a question. The first pop quiz, first one. So the first test series were in Frenchman Flat, out on the test site, which is a dry lake bed. Anybody have any idea of where the name Frenchman Flat came from? Close, but no. There's a book out there called Origins of Names of Nevada Places and Names. And someone asked me this question. I said, I don't have any ideas, but I found this book. And in there it states that in the 1800s there was a Frenchman who guided people across the Santa Fe Trail. Southern leg of the Santa Fe Trail actually went across the southern part of the state. And for some reason, someone decided, you know how those things happen, that they should call this Frenchman Flat. At least that's what the book says. The base camp in where things all pass through going to the test site at the very southern edge is called Mercury. Any ideas how we got the name Mercury?
It's poisonous.
Huh?
It's poisonous, and so is nuclear testing.
Sounds like a good answer, but no. Actually, what they found, and how the name came about is after they decided they were going to be permanent, they needed a post office. So whoever was in charge of the test site sent one of his assistants to town to get a post office established out there. So the guy goes into town, he deals with the post office, and he comes back and tells his boss, we have a post office and we're called Mercury, Nevada. He says, well, wait a second, where's Mercury? Where did you come up with this? He said, well, you can't have a post office without having a name for that post office. So I figured since we would find these little mercury containing vessels out there, because there was a few gold and silver mines, which you use that for algament, that we should call it Mercury. So I said, my choice, I decided it's Mercury. So that's how Mercury got its name and continues to have its name. As you can see, the name of the test site has changed over the years. It started actually out as the Nevada test site and then almost immediately the Nevada proving grounds, and then went back to the Nevada test site. Big controversy. Everybody said, oh, it's a proving grounds, blah, 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 blah. Blows over. Well, 2010, they changed the name now to the Nevada National Security Site. Again, the same thing. All us people who worked on the test site for years and years and said, oh, no, it's always a test site. So I retired in 2008, so I'm still allowed to call it the Nevada test site without repercussions. Some facts and figures about testing. You can see where various and sundry tests were taking place. Again, this is atmospheric from 51 through 62, except when we had a moratorium in here from late 58 into late 61. Underground testing from actually says 61 into 92. And we did tests in other part of the United States for what was called the Plowshare Program, peaceful use of nuclear explosives type of thing. We quote, we want to change the Panama Canal, we can dig the canal with explosives, that type of thing. Oil fracking or gas fracking. Statistics, 210 above ground tests conducted. 839, actually the test site was 828. Underground tests and exactly 100 above ground tests at the test site. I'm done. Questions? You know everything about it now.
What did you do at the test site?
I started out as a diagnostic engineer, running recording stations, doing high-speed diagnostics. I'm talking about things in the nanosecond or 1/1,000,000th of a second time range, sub-nanosecond things. I've been the operations manager of the test site. I was over at Nellis for a remote sensing lab as their lab director over there. Lots of various sundry things, but my background is I have a undergraduate in electrical engineering with a physics minor, and then I have an MBA. So did lots of various things. Very interesting work. State-of-the-art cutting technology, still is that cutting technology out there. And that's one of the things we're looking to do here in the museum, is to let the public know what's going on at the test site now. Probably one of the most frequent questions we get. So you did the last underground test in '92, test site closed, what are you doing? And that information is just not out there. It's not secret or anything. People just don't seem to want to talk about it, but we do. Other questions? Jack?
Right.
You're on.
There were a couple questions right
Oh, I can't see in the,
Why did the
is just not out there. It's not secret or anything. People, well, I don't have to go 2,500 miles one way to get back. Also, I don't have 42,000 people that I have to pay to do that. The test site in its heyday had 10 to 12,000 people who worked out there, but that's a significant difference. And as you do something over and over, you get better, you get more efficient at doing those type of things. Again, still an expensive business. So, another question? Difference, and as you do something over and over, you get efficient at doing those type of things. Again, still an expensive business. So, another question? Personal opinion. Okay, I have to say that. I think it's safe. We're underground. Back in 1970, we had a test called Bainbury. I don't know, probably not many of you around. Bainbury was a containment failure and spewed out a big crowd. In fact, I think we have a picture here in the back, and we talk about it. But that caused us to look at our whole way we do containment. We stopped testing for 6 months. In fact, we didn't know whether we were going to go back to testing after that. But completely reevaluated, revamped how we do it, and we have not had a test that went, or a vending that went like that. In fact, we haven't had any releases that you would see at all, except every once in a while you get some noble gases which will seep out. Primarily due to, and it will happen after the test, atmospheric changes, you get a lowering in the atmospheric pressure, and you will get some seepage out, but it doesn't go anywhere. It's noble gases, so it really doesn't cause any issues. Can't say that if you had to do an atmospheric test. Completely different story, because you can't control where that's going to go, even though you've got great weather predictions and you know what the weather's you think you know what the weather's going to do, but you're still spewing radiation out. In fact, the tests I'm talked about in specific, we had a test called Castle Bravo in 1954. Supposed to be about 6 megatons. Notice I've changed from kilotons, thousands, to millions of tons of TNT going off, because that's what you get when you go to a thermonuclear or hydrogen device, that much more energy release. And they didn't understand the physics in the hydrogen part, and so instead of being 5 or 6 megatons, which you choose, it went over 15. Obviously, the containment area they had designed wasn't big enough for that. Caused all sorts of problems, and was probably the catalyst for actually to sign a treaty with the Soviets and the United Kingdom in 1963, limiting testing to only being underground. Before that, we had tests in the atmosphere, we did a few underwater, we did things in outer space. That treaty prohibited us from testing except underground, and we had to contain it, and it had to stay within your country's boundaries besides that. China didn't sign on to that, and obviously China tested after that. Same way with India and Pakistan, and obviously the North Koreans. And actually the French did. The French did some tests in mid-90s, but they were underwater because they tested the South Pacific and down off one of their islands in Morale. The French did. The French did some tests in, but they were underwater because they tested the South Pacific and down off one of their islands in Morale. Long answer to your Koreans. And actually the French did. The French did some tests in, but they were underwater because they tested the South Pacific and down off one of their islands in Morale. Long answer to your Koreans. And actually the French did. The French.
Is that on one? Yeah. Okay. Had to put a new battery in it earlier. So, since '92, any of the testing that we do out there does not produce nuclear yield. And furthermore, when we do testing out there, which we are doing, it's limited to very small quantities of nuclear material and explosive that is totally contained over 1,000 feet underground in a special test facility that we've developed. That's a deep underground tunnel that's very long with a lot of side drifts off of it. And so we'll do a test in each side drift, and once that test is done, it's sealed off, concreted in, and we make no attempt to re-enter the area where the test actually was conducted. But these are what I would call physics tests to determine better numbers for our supercomputers at the 3 weapon labs at Los Alamos, Lawrence Livermore Lab, and Sandia. And these are the 3 labs that do our development of nuclear weapons. Now the ones that develop the designs are Los Alamos and Lawrence Livermore. Sandia takes those ultimate designs and weaponizes them. So the kind of tests they get involved in are generally with the Defense Department to be sure that this weapon is going to mate up with whatever delivery systems we're going to put them on, submarines, aircraft, other things. We're going to cover a lot more of that kind of thing when we get in the museum and are walking around in a few minutes. So let's hold off on that kind of subject. I want to talk for just a very few minutes about how we measure radiation and understand that we've had radiation instrumentation since we started the whole business. In fact, since before even the U.S. was involved, the Europeans, because if you're going to do anything with nuclear interactions, there's no smell, there's no taste, there's no other sensory kind of a thing that you get from it, so you have to have an instrument to know what you've done. So we developed these various radiation instruments, and obviously, as in any other technology, as time goes on, they get better. And they get better for a couple of reasons. One, as technology grows, we're able to move to much smaller, more compact instruments. These things used to be 2 to 3 times as big and heavy, and now you've got something you can easily carry around. Your actual sensor is this thing up here, and that varies too. You can have systems that are electronic like that, or you can have an actual sodium iodide crystal on there that is like a big salt crystal that has a photomultiplier tube attached to one side of it. And whenever radiation strikes that salt crystal, you'll see little flashes of light in there, but you don't actually see that because it's completely enclosed. But the photomultiplier tube sees that, and that signal then is processed by whatever instrument you have. The other thing that we learned from that, what these instruments do is you'll hear the usual clicking sound that you've seen on every movie about people measuring radiation. And we'll turn these on in a minute. In fact, I'm going to invite all of you to come up here and do these yourself. But you hear that count rate, that clicking, the counts per second is telling you something about how intense the signal is. And of course, it matters whether you have it set on ×1 or ×10. And you can think you've got a really big thing when you're really looking at a very low signal. The other thing that you can't do with these kind of instruments is you can't tell what the source actually is. You can make some educated guesses about it, but to do that you really need a spectrometer. And when we started this business, there were no spectrometers out there. We have one of the serial number ones that we built for our own use, and now industry today has built them. And this was a battery-powered unit that we could take out in the field with us, and it would look at the energy spectrum. So you're really looking to understand radiation. You got to look at two things: one, how intense it is, the count rate, and the other thing is to look at what energy it is. And the energy numbers relate very clearly to what isotopes we're dealing with. Now, like anything, everything's messy. There is a natural background radiation that you start out with that produces in the low energy into the band a lot of noise. And then you may have a signal that's in that noise that's hard to pick out. If you have like cesium-137, which is a source that we run into with medical isotopes and with industrial gauges and these sorts of things, that one is a higher energy peak, and it really stands out. So, and it's out in a part of the spectrum that is low background, so we can actually see that rather easily. So with these instruments that we have up here, we've got some typical sources that you run into, and I'd like to get everybody to come up now, and we'll try these things out. Let me get Jordan to come up here and help get them turned on for us. Now we've got some things out here that may not look like sources, but if you hold one of these instruments close to one of these things. Now, we use that little dim, this is the sensitive side over here. Yeah, yeah, come surround us here. Is that one on?
This was commonly made in that red paint with uranium. And then we found out it was radioactive. That's pretty cool.
Yeah, now, a couple of things that you need to know. You might dump those green rocks out on the table and then put your instrument on the rocks. Not getting anything. Put them on the bowl. That's a piece of Fiesta ware, and at one time that was quite common, and you may even have some at home.
Oh, it's still a big
But
thing.
that orange is done with the uranium oxide to get that orange color, and therefore it's radioactive, and it may also have a fairly high radium content, and radium's a much more dangerous isotope to worry about, and it's not a good idea to be eating food off of that kind of thing. Now, today's Fiesta ware does not use the uranium oxide. They can still get colors, but if you get some that's in an antique shop, you could very easily get one. Now, these little cups are where?
It's Vaseline glass, so it's uranium is in there.
It's uranium.
Yeah. Now, and the clock there is got a radium dial on it. So the dial on that clock is radium.
Oh, yeah. Buy one of their tools for your auntie.
So how do you count it when it starts going crazy like that?
Well, you may have to change scale and take the reading of what you're seeing there, but again, until you know what isotope you're dealing with, just because it's loud, high click rate doesn't necessarily mean run for your life.
Yeah, right.
As in the
Now,
movies, where it goes, like it goes crazy and people are like, oh my God.
for those of us in the business over the years, you know, you get sources, and these aren't the ones that you need to take with you on an operation, and you'd like to have one that doesn't require being controlled the way it's required today with every source.
So is there, on this little gauge,
You know what that is?
are there different,
It's lead.
like if you found lead, would it read differently here than if it was?
It'd be much lower signal,
So it'd be
but it
lower.
would read the same as these other things are that we're
But the
looking
signals
at.
would be different
Yeah.
depending on what.
The input not going to differentiate the count rate
Okay.
for anything. So the kind of source that we used for years was, if a camper been out camping, this is a Coleman mantle
Oh, yeah.
that you put on a camp. We discovered, they probably knew it all along, but they coat that with thorium, which is, and then you burn it on your mantle to an ash. It's still hanging there in one piece, and it makes the lantern glow a very, very bright white light for you. So it makes a really nice camping light. Then once the word was out that this was radioactive, for a period of time they switched and made some mantles, some company that had no thorium on them. And all the people, campers and hunters, scouts and what have you, complained that this lousy thing doesn't make enough light. And so they went back to the thorium coating, because it was the only thing they could find that would make the bright white light that this does. The only thing I would suggest to you is, if you're a camper and use these, you have to light it and let it turn to an ash. It'd be a better idea not to lean over the top of the lantern while that's burning, because your greatest hazard from something like that is inhaling radiation from any of these kinds of sources, because once those fine particles, and we're talking things that are in the respirable range, 3 to 10 microns, which is a very indeed, that's all you'll actually inhale. Anything else outside of that is too big, and you'll reject it, or if it's smaller than that, it goes in and comes out. But in that range, then it is in your lung. And in your lung, then it can do really serious damage, because it's right there. There's no distance, it's zero distance. And so the radiation from that particle can hurt you. And it might be interesting to know that the smoke in cigarettes has a certain level of background radiation also. So you're not just being poisoned by the chemicals, you're being had by the radiation aspect as well. Yeah. The final thing is, if you're really freaked out about radiation and whether things might be getting you, you can find little instruments like this on Amazon, and it's a counter like these, and those. But if I look at my mantle here, or look at one of these other. Oh, that's a radium painted dial. And back in the day when they were doing radium treatments, or even before when they were doing these, the radium dial painters became a long study, because they would dip their brush in the paint to paint those kinds of things, and they would lick the brush, and many of them died a very excruciating death as a result of that. So These are just some of the instruments that can be used for making radiation in the museum. We'll show you an exhibit that we have where you can buy and actually do hands-on with an instrument like that with some of these same kind of sources in our little demonstration area. But it's easier just to see them out in the open like this. And we're careful with these, but they're not anything you need to run away from or anything like that. To realize that radiation is in the soil and the ground everywhere. You're being bombarded by cosmic radiation coming in from outer space. So you that. The other thing is, in some parts of the country, radon is an issue, which is a radium gas that can come out of the ground. And when the air pressure changes, if you have wells drilled or whatever, you can have an increase in the level of the radon, but that takes very sensitive measuring equipment to see that. Now I know that with our aircraft that we had, and I managed the group at the remote sensing lab for 28 years, and in that one we actually could see, when we were flying over wells, we could see the radon bump coming from those wells depending on what the air pressure was doing at the time of our flight. The purpose of our aircraft originally were to be in the air every time we did a test, so that if we had a release or something like this, we could track that and see where it went, because under the treaty, we needed to certify that it stayed in the boundaries of the United States. In the case of that Bainbury thing in 1970, I was in the control room at the test site when that venting occurred, and we had our aircraft in the air, and by rotating aircraft, we tracked that cloud continuously across the United States. This was December 18th, on the day before Christmas. We finally were losing track of it over Pittsburgh, Pennsylvania, and put our crew on commercial flights back to Las Vegas for Christmas, and they had to go back and get the airplane. But we argued strongly that we shouldn't do a test that close to Christmas anymore. Not that that got listened to, but that was one of the factors. And of course it did shut everything down, as Nelson said, for like 6 months before they came back. One other thing about radiation, kind of a basic physics thing that, you know, after a period of time of working with all this, you know, there's whenever you open a can of worms, it always takes a bigger can to recan them. Because as soon as you discover radiation, you have to follow it up. And with our aircraft, we often would find radiation sources out in the public that people weren't aware of. We discovered at the Harshaw factory that was making the thorium back in Illinois that they had areas of a small town where their factory was, where the ash piles from their production were highly contaminated with that, and we mapped that for them, and then the local health authorities had to work with local government to figure out what to do with them. And Harshaw, of course, was in the middle of helping clean it all up. But over the years, we've discovered if you're making real low level measurements out in the public, you're going to find sources. Even things like whenever my cardiologist has said I need to do a full stress EKG, he will inject a real short half-life isotope in order to make that measurement, so that they can see what's going on with your heart and related organs. And whenever I did those, I had to carry a letter with me, so that if I went out to the test site, when you drive into the test site, we've got monitors, and they'll light up quite well when you drive in there. And you better have some documentation to prove what you did, or you could spend the whole day locked up being interrogated. And it turned out there are other interesting places in the U.S. where there's monitors that we only happen to learn about casually. The other thing where surprise sources will show up, it turns out that the granite comes from the White Mountains in New York and is used for an awful lot of statues, particularly in Washington, D.C., but all over the country. That those little black specks in that granite are hornblende, which do contain uranium. And I personally measured one statue in the foyer public area of the hallowed halls of Congress that was 100 times background. And so those things are out there, they're everywhere, they're not going away. It's not out of the ordinary in some parts of the world to have things that'll be maybe 400 times higher. And so we do get excited when we hear these things clicking, but that really doesn't necessarily mean that there's danger. You've got to have trained health physics people that can come in with a spectrometer and identify what the isotope is. Maybe it's something that's easily removed, but it may be a lot more complicated than that. So with that, any questions about any of this? It's a very quick demonstration of just the instruments and the kind of things. Now, with some of the instruments, you'll see some that have a cylindrical detector with a metal sleeve that has slots in it and rotates. What that'll let you do is differentiate between, you've got the basic three types of radiation, alpha, beta, and gamma. And with that instrument, you can differentiate between alpha, beta radiation and the pure gamma radiation, if that's the kind of source that you have. And so that will let you maybe eliminate some sources. You can shield the alpha radiation with a sheet of paper or even your clothing. The beta radiation will take something more like foil, aluminum foil, and gamma radiation is gonna, best defense there is distance, get away from it. And but you can use concrete, you can use other, water turns out to be a really good shield. So if it's put down in water or in a barrel of sand or something like that, that protects you from that pretty well too. Keep in mind though that sometimes the hazard of these things is more from other factors than just the radiation. In the case of uranium, for example, just natural uranium that you find, keep in mind that that is a very heavy metal, and so you have contamination there that is toxic from a heavy metal standpoint the same way that lead is. And so you wouldn't want to ingest any of that any more than you would want to ingest lead. And so it's best if you have those things to just have them in Ziploc bags or wrapped in various ways so that you don't actually get direct skin contact with those things. So that could come up too. Okay, let's go.
Before, Jack,
Yeah.
I took my mic off, but can you hear me?
Yes.
Okay. Before we go into the museum, let me give you just a couple of minutes of history associated with getting into nuclear weapons. Back in 1938, in Nazi Germany.
Translator, and I said, hey, tell them all the original documentation for our nuclear weapons program and theirs is in that building. They didn't translate that. But anyway, as we continue on, the Soviets have an atomic bomb now, and again, they don't. It's not just an atomic bomb. It's not just a copy of theirs, but now Joseph Stalin has an atomic bomb as well. And of course, as the 50s progressed, these fears, which were totally legitimate, were stoked by the bomber gap. We thought the Soviets had 800, 1,000 atomic bombers that were going to fly over the North Pole and destroy us. The missile gap, we thought they had more and better missiles. And Sputnik, which I will only mention in passing for now, but Sputnik is going to be an important part of our story as we go through it. So next, let's go back to building nuclear rockets. What you see up there, you see a couple of Manhattan Project veterans, Los Alamos Manhattan Project veterans. So John von Neumann, famous Hungarian mathematician, he was at the heart of the implosion program at Los Alamos during World War II. After the war, he became an advisor to the Air Force. The Air Force is interested in delivering hydrogen bombs, big, giant, heavy hydrogen bombs, maybe using means other than a big, lumbering, heavy bomber. So he thinks, well, this nuclear rocket business that people have talked about, I think I may have an application for it. Now, his advisory panel to the Air Force included another project veteran from Los Alamos, Darrell Frohman. So Frohman's in charge of the reactor division at Los Alamos. So you can kind of see where this is going. These guys start talking about the possibility of building a nuclear rocket engine. Now, there's one issue, though. Los Alamos, at that point in time, was a nuclear weapons lab. We did almost nothing besides nuclear weapons at that point in time. Of course, today we're a multidisciplinary institution. Back then we did nukes and a couple of other things that were kind of for nukes anyway, right? So what's the director going to think when we come to him and say, well, we want to get into the delivery system business? Actually, the director at the time, who our museum is named after, Norris Bradbury, he thought, this is a pretty good idea. Not only is it cool and useful and nuclear weapons related, but you know, we probably should start technically diversifying the laboratory. Because nuclear weapons might go away at some point. Or at least the research, all the effort that we put into it may get a lot easier. So that's the thought. We'll talk about that a little bit more in just a moment. So that's how this program starts. It becomes, well, initially, it's just a little group. So Frohman comes back, sets up a little group. They're going to call it the Condor Committee. We're going to get together, talk about this stuff a little bit. That next year, in April of 1955, less than half a year after the Condor Committee was established, Norris makes this a division-level activity. He creates the Nuclear Rocket Propulsion Division, and it is led by yet another Project Y veteran, Raymer Schreiber, who you see over there. Schreiber has kind of been lost to time. Some of us still know him well back in Los Alamos. I think the documentary was recently made, so you might look that up if you'd like to learn